Okay, so once again, we're bumping the exam and we're moving it, and we're going to take it on Thursday instead of Wednesday tomorrow. So you're taking it on Thursday, the 9th of April. And again, you can take it anytime on the 9th, and same directions as it was for tomorrow, that it will be for 2 days from now. So instead, we're going to go on in chapter 4, and we're looking at the techniques that we just used, finding derivatives, to help us graph a function. And so 4.3 talks about using the first derivative to graph functions. Okay, so we're jumping into 4.3. And we're trying to find where a function f of x is increasing and decreasing. So a couple of things have to hold when we're looking for where it's increasing and decreasing. So we need to know what the domain of our function is, because obviously it's not going to increase or decrease if that's not part of the function that's undefined there. What else do we have to do? We also need to find out where it's defined, because if we have asymptotes, we might be increasing on one side and decreasing on another. The other thing that we need is it has to be differentiable. Okay, so let me just give you a rule. I'm gonna just use this as a guide. Okay, so here is a corollary. Okay, so corollary is like a theorem, but maybe not as strong or as big as a theorem. So we're going to suppose that you have f is a continuous function on some interval AB. And it's differentiable everywhere inside that interval AB. So we can say the following: if f prime of x is greater than 0 at each x values contained in that interval where it was continuous AB and differentiable, then we can say that our function f of x is increasing. On AB.
I'm sorry. For what's in bold, what is that?
Corollary. So corollary.
Okay.
Yeah, and I don't think I ever really used that word before in here, but basically it's like a theorem. But theorems are usually bigger and have more going on.
Right. Okay.
Yeah. So it's something that's been proved, that this has been proved that this holds true always, if these conditions hold true.
Kind of cares about the history behind it.
You find out and let me know.
Yeah.
So if you look at the derivative, or you choose any value in between that interval, a, b, and you plug it into your function, the first derivative. So if f prime of x is less than 0 at each same kind of idea as above, so for each value of x contained in AB, then we can say that our graph of f of x is decreasing. On AB. Okay, so I'm not going to go through the proof of this, but this is something that's going to really help us figure out. So we can now figure out where our graph is increasing and decreasing. And based off of where it's increasing and decreasing, we can also find local maximum and local minimum points if they occur. Okay, so let's say that we had some graph. And let's say we had some values, I don't know, A, B, and C. And we plugged in some value of X that was contained on the left of A. I don't know. And let's say we plug that into the first derivative. And we found that plugging that number in, we got a number that was negative, number less than 0. That's telling me that my function on the left of A is a decreasing function. If we chose some number in between A and B, so let's just call it x sub 2, and we plug that into the derivative, first derivative function, and we saw that that value was positive, so it was greater than 0, then we can say that our graph is increasing here. Let's say we chose some number in between B and C. Let's call it x sub 3. And we plugged in x sub 3 into the first derivative. And we found that it was less than 0, let's say, then we would know that it's decreasing in here. And one more, if we plug in a number to the right of C, so let's call it x sub 4. And we found that plugging it into that number into the first derivative, let's say we found that that was greater than 0, then it would be increasing here. Okay, so remember, taking the derivative, that's representing the slope of our function at a particular value on the graph. And so if we're getting that we get our slope is negative, we know our function decreases. You know, if our slope is positive, our function is increasing there. And so if we can find out where our function is increasing and decreasing, we can also find other important parts. So notice on our graph where if I had something that was decreasing and then changes direction to increasing, what type of point could be occurring at A? So at x equals A, so again, if you have something that decreases and then comes back up and increases, what type of point is that? So this would be a minimum value. Okay, so these are all they could occur, and we'll look at noticing if they're really occurring there or not later. But notice that x equals b. So from the left of b, we had something that was increasing. Let me see. So we had something that was increasing going up, and then it changed directions at b, and then it started decreasing. So at x equals b, looks like a max can occur. And so we can do the same sort of reasoning for C. So if we have something that is decreasing on the left of C and then increasing on the right of C, then it's possible, but not necessarily true, that that is a min at x equals C. Okay, so the first derivative is going to help us find where our graph is increasing and decreasing. It's also going to help us find where local max and local mins occur. Just want to kind of give you a couple of examples. So let's say this here was A, and we had something that was increasing, like I said, or I don't remember. And then it changed direction, and then it is decreasing. Okay, so remember, you're just looking left to right to see, is it going up left to right or coming down left to right? So increasing to decreasing, but notice that x equals a, that's an asymptote. And so here's a point where x equals a, it's changing directions on either side, but a max or a min don't occur. It's also possible, and we're going to be finding out where these max and mins are, or it's going to help us, or where it's increasing or decreasing. Values would set our derivative equal to 0, right? Because we saw that max and mins always occurred unless it was on the endpoint of an interval where it was increasing or decreasing. So notice here, right, if I was looking at the equation, if I was looking at my tangent line, we know at the tangent line here, at the max, and the tangent line here at the min, we know that our derivative is equal to 0. And we talked about that, I think, in the first section. So local extrema could occur when the derivative was equal to 0. The problem is local, you could get your derivative equal to 0. So here's an instance. But where it's equaling 0 here, notice it's not changing direction. It's still strictly increasing. And so this value here, I don't know, x equals c, is not an extrema. Questions on that? Okay, so first thing we want to do when we're looking at where a graph is increasing and decreasing, we want to figure out when is the first derivative equal to 0 and when is it undefined. So to find when a function is increasing and decreasing, we want to find the first derivative and find the values where the first derivative is equal to 0 or the first derivative is undefined. So these are called our critical numbers. So we pretty much did this before, I feel like. And then once you find your critical numbers, you're gonna put the critical numbers on the number line and test a number on each side of a critical number. And we know that if the derivative was greater than 0, it's increasing. And if it was less than 0, it's decreasing. So let's look at an example. Okay. So this, so how about g of x is equal to x all times the square root of 8 minus x squared. And I want to find where g of x is increasing, decreasing, or constant. Okay, because I have a radical in here, I notice that my domain possibly is not everywhere. It isn't everywhere. And so I know that my domain is a not negative infinity to infinity. So it will be helpful to figure out what the domain of f of x is. So let's first determine the domain of g of x. And so because of the radical, I can't have negative numbers underneath that radical or I don't get back a real number. And so I know I need the values underneath that radical. 8 minus x squared has to be greater than, and it's okay that it's 0, because I can take the square root of 0. It's a real number, it's 0. So I noticed that my 8 minus x squared has to be bigger than 0. Okay, so this is bringing back college algebra stuff. So if it's nonlinear inequality, which this is nonlinear, we didn't solve it like we would solve a regular linear inequality. This is where we had to find our critical numbers again, and then we would test to see if it was positive or negative, making this a true or a false statement. And so if I factored this, so if I looked at when is 8 minus x squared equal to 0, I can manipulate this to look like a difference of squares. And so that's going to be a trick that you're going to start using in math. So instead of, I'm thinking of a number that I can square to get me 8. Well, isn't the square root of 8 times the square root of 8, 8? And so we can break this down as the square root of 8 minus x, all times the square root of 8 plus x. So solving for the values which make that equal to 0, I'm looking at when is square root of 8 minus x equal to 0, and square root of 8 plus x equal to 0. So that would be when x is the square root of 8, or when x is equal to negative square root of 8. So if I looked on my number line, so negative square root of 8 and positive square root of 8, I'm not even doing any calculus right now. I'm just going back to algebra. I want to see what values would give me positive numbers and which values would give me negative numbers. So I notice if I plug in something less than this, it's actually giving me a negative number. So if I plugged in the square root of negative 9, I'm going to keep it as the square root of negative 9, and I square that, well, square rooting a negative is positive. So that's going to give me positive 9. And so I have 8 minus 9, that's a negative underneath the square root. And so this is a false statement. And I know I can't have any numbers which are less than negative root 8 in my domain. I also see if I plug in 0 in here, underneath the radical, I get the square root of 8, which is positive. I can have that. And so I know that any number between negative square root of 8 and positive square root of 8 is in my domain. Same reasoning as on the left of negative root 8, same thing with on the right of positive root 8. When I plug it in, square it, and then subtract it, it's going to be bigger than 8, giving me a negative underneath the radical. And so this cannot be part of my domain. And so I know my domain is between and including negative square root of 8 to square root of 8. Okay, so why would that really help me? The reason why this could help me is later on when I look at the derivative and I find values which set it equal to 0, if it's outside of this domain, then I don't have to worry about it. So let's now use our calculus to find where it is increasing and decreasing. And so again, we're going to do that by looking at the first derivative, and we're looking at when is that first derivative equal to 0. So looking at this g of x, so here's some review for tomorrow, or not tomorrow, Thursday now. Looking at g of x, I notice I'm going to have to use a couple different properties. I'm going to have to use my product rule, and I'm going to have to use my chain rule when I take this derivative of the square root of 8 minus x squared. Okay. That's not what I wanted. That was from the last class. Okay, so like I said, product rule, product rule and chain rule. And so first derivative. So it's the derivative of x, which is 1, times the second piece, which is the square root of 8 minus x squared, plus the first piece, which is x, times the derivative of the square root of 8 minus x squared. So think of that as a power, 1/2 power. So if you bring your power down front, 1/2 of the inside, 8 minus x squared. Subtract 1 from the power. So it's going to give you 1/2 minus 1 is negative 1/2 times the derivative of the inside. So the derivative of the inside, 8 minus x squared, is negative 2x. So I want to clean this up a little bit. And so this gives me the square root of 8 minus x squared plus, so notice here I have a 2 that's in my numerator, this negative 2x, and I have this 2 from the 1/2 in my denominator. So those go away. I also have this x out here times this x here. So I have an x times a negative x. So this is going to give me actually a minus x squared. And then the only other piece that is left is that negative exponent. I'm going to bring it down to the denominator and put it underneath the radical. And so critical numbers occur where this is equal to 0 and undefined. Okay, so I'm looking at that equation, and now I need to set that whole equation equal to 0. Okay, so I also notice I have radicals, I have stuff in the denominator. I could multiply everything through by my denominator. I can do that because this is an equation. Whatever I do on one side, I do on the other to get rid of that denominator. Also notice that's going to help me get rid of this radical too at the same time. So let's clear the fraction by multiplying both sides of this equation by the square root of 8 minus x squared. And so when we do that times the left-hand side times 0, we just get 0 equals, well, a square root of 8 minus x squared times the square root of 8 minus x squared is just 8 minus x squared. Minus, the whole point of this multiplying was to get rid of the denominator, so that cancels, leaving you with just the x squared in the numerator. So that doesn't actually look as bad as the original one. And so we got 0 is equal to, got like terms. So we have 8 minus x squared is minus 2x squared. If we add 2x squared to both sides to solve for x, we get 2x squared equals 8. Divide by 2, we get x squared equals 4. I can set that equal to 0 and factor, or I can use the square root property. Don't forget the plus or minus in front of the radical. And so we get x is equal to plus or minus 2. Okay, so actually I need to make sure that that is in between square root of 8 and, or sorry, negative square root of 8 and positive square root of 8, which it is. So we're okay. Same idea, it's undefined, same place that our original function was undefined. And so technically we're looking at the following. So we have an inbound on our interval of our graph is negative root 8. We want to see what's happening in between negative root 8 and negative 2, because that's one of our critical numbers. Then we need to see what's happening between negative 2 and 2, because 2 is one of our critical numbers. And our inbound stops at square root of 8. Okay, so there's 3 different numbers that we need to check because there's 3 different intervals, and we're plugging this back into our derivative function. I'm just seeing which is the best to plug it into. I was thinking to myself, oh, I'm getting a little bit better at this. And then I shouldn't have thought that. So that's our derivative, test our values. And so anything between negative root 8 and negative 2. So negative 3 falls in between there, does it? No, it doesn't. Let's figure out what square root of 8 is. I know it's 2 root 2. So that's 2.8. So a number that falls in between negative 2.8 and negative 2. So how about x equals negative 2.5? So we need to see if we plug that number in to the derivative, is it positive or negative? I don't care what that number is. I just care, is it positive or negative? So let's see if we can figure that out without figuring out what that number is. Well, if we square negative 2.5, I know I get I get back 6.25, and it's going to be positive. 8 minus that 6.25. Well, actually, we know our square root's always going to be positive, right? Because we chose numbers that were in our domain. I can't get a negative number in here. So this is always going to be positive. So let's reason that way. Minus, I know, so again, that square root's always going to be positive. If I plug in negative 2.5 and I square it, well, that's going to be positive. Which number is bigger? Well, this would be the bigger number, right? Because you're dividing maybe. Okay, so I was trying to do all the reasoning without having to plug it into the calculator. How about this? Let's use good old Desmos. Actually, I just did the wrong one. Maybe not. Okay, what do we have? We had the square root of 8 minus x squared. Minus x squared, all divided by the square root of 8 minus x squared, all raised to the 1/2. So if we plug in negative 2.5, this should spit back what my answer should be. So that gives me negative 3.4. So let's just do it this way. This is approximately negative. I think I said negative 3.4. Anyways, it's less than 0, and so it has to be decreasing there. So choose a number on the right of negative, between negative 2 and 2. So 0 falls there. Well, if I have 0 squared, that's 0. And so g prime of 0. And this will be minus 0. So this is going to be a positive number. It's going to equal the square root of 8. So it is increasing on this interval. So choose a number between 2 and square root of 8. So we know that 2.5 is in between there. And so if we look at the first derivative, plugging in that value, we want to see is it positive or negative. Well, if you look at our function, wherever we plug in x, it's a squared function. So that should give me the same thing as when I plug in negative 2.5. And so that should be less than 0. So it's decreasing. Okay, so we just found the intervals where your graph is increasing and decreasing. So it's increasing in between negative 2 and 2. It's decreasing between, it's including the inbound negative square root of 8, comma, negative 2, but we don't include where it changes direction. Oops, union. It's also decreasing at 2, but it's starting not at the end point of our interval. So it's a parentheses 2, comma, square root of 8, but bracket because we're stopping at square root of 8 in our part of our domain. I'm like hearing some funny sound and I don't know if it's our refrigerator making noise. It might be my son making noise. I don't know. Anyways, trying to figure out what it was. We're almost done. Let's just look at this problem real quick and notice that you could tell that we have something that from decreasing to increasing, x equals -2 should be a minimum point if that's defined in our original function, which it is. And it's increasing from -2 to 2 and then decreasing, so that should be a max. So x equals -2 is a minimum, or a min occurs. And at x equals 2, a max occurs. And so remember to figure out the max or the min value, you plug that back into the original function. Okay, so I'm not going to do that just because time is pretty much up. So we got through one problem. Let me pause the video. So again, the test is going to be on Thursday instead of tomorrow, Wednesday.